Okay, welcome all. Today's lecture is based on the device fundamental explanation of Zener breakdown and Zener diode. Okay, so whenever a PN junction is reverse biased, so in power device we all know that this IVD, so voltage across a diode, the current is ID and voltage across is VD, then the curve look like this. Okay, and in reverse bias it is almost like reverse saturation current, IS. We all know this very famous equation, ID is equal to IS exponential VD upon VT, where VT is at room temperature, it is 26 milli electron volts minus 1. So when this VD is negative, of course you can see that ID goes to minus IS for VD greater than, or you can say that technically less than minus 0.1 volts. Okay, so ID goes to approximately equal to IS. Now the question is that in reverse bias whether this current will continue to till infinity or what. If we are going to increase the reverse bias, that means positive is connected to negative potential and N side is connected to the positive potential. To answer this question, let me tell you that as we are increasing the reverse bias, what's happening is that we are establishing externally an electric field like this. Okay, but still these junctions are actually quite strong and they try to stop any carrier movement, that means P from this side or N from this side into motion. Okay, because of the internal structure of diode, which we all know. Right? Sorry, so N from this side and P from this side. Anyway, but we are already increasing the pressure. Okay, as we are increases, this pressure increases, and there will be a time when this junction will not control this pressure, and the current will go in negative direction. That means after that this current will increase. ID that will increase, of course, in negative direction, because conventionally we are taking ID positive in this direction. Okay, why? Because of two breakdown mechanisms. One is called Zener breakdown, which happens because of the tunneling of valence band electrons into the N-side conduction band. So tunneling current, because of tunneling current. And this happens between 2 volts to 8 volts around. Okay, not more than that. Another mechanism is avalanche breakdown, which happens because of the process called impact ionization. What is this? I will let you explain in some other lecture. Anyway, so this diode breakdown generally can be characterized in two major categories: Zener breakdown and avalanche breakdown. The effect is that a large number of carriers will move in this direction and this current will flow. So this junction will no longer stop the pressure of this applied reverse bias. In Zener breakdown especially, putting this on the other side. In Zener breakdown, what happens is that if you see in terms of energy band diagrams, N type and P type, they are heavily doped. So let's say P is equal to 10 to the power 18 and N is also equal to 10 to the power 18 approx. Because these carriers are quite high, that means ND is equal to 10 to the power 18, Na is equal to 10 to the power 18. Because of high carrier doping, the width, this junction width, that is quite small. So very small region around the junction that can provide the balance for this. So just to balance this built-in potential. So this W is very small. Of the order of few nanometers. Still at this position in normal condition, tunneling cannot happen. As I have said that Zener breakdown is because of tunneling. Normal at B bias is equal to 0. This is the energy band diagram. However, if you increase the reverse bias, the whole this energy band diagram that will shift down, right? And the energy band diagram may come over here, something like this. So EC, EB, and EF. Of course, this width will also increase with reverse bias, and the total built-in potential that will increase by BBI plus BR. And this junction will be, something like this. Now what will happen is that most of the holes over here that will be concentrated just below the valence band. Okay, so at the top of the valence band, all the holes will be there. What all these areas, they are filled with electrons. Electrons, that is the lattice electrons in valence band. So lattice electrons in valence band, you can understand like this, that each silicon atom, they are connected with other silicon atoms in lattice, right? So these electrons, which they are actually forming the covalent bonds, they are valence electrons. Of course, they are of the order of 10 to the power 22. In this side, most of the electrons that will be near EC. So all these free electrons which we are talking about, so they will occupy energy state just above EC. Most of the area that will be vacant in this region. This region, most of the area are vacant. Now you can see that because this width is very small, there is a high number of electrons in the valence band of P side, and how empty is a very large number of empty states on the N side for the same energy level. So here comes the theory of tunneling, that if an electron which has, or a particle which has energy E and is isolated with some very small distance d, and the energy corresponding to that area, if that is same energy level, that is empty, if this is empty state, then this electrons can occupy this location with some finite probability, and the tunneling probability is proportional to e to the power minus t by some constant. Okay, so this lambda naught, that will be okay, so lambda naught divided by, you can like it, lambda naught, that is proportional to root over 2 mu minus e divided by h square. Okay. So don't worry, this is a constant for a given scenario. The objective of this discussion is that as d reduces, this tunneling probability increases, and that's the same thing which happens over here. So these two conditions for tunneling, number one is that on one side we have plenty of electrons, other side we have plenty of vacant seats, and they are separated by very small distance w. That can be achieved only in case of when these doping concentrations are quite high. So for w to be minimum, this Na Nd, that should be very high. So of the order of 10 to the power 18. If this happens, this W comes into that region where this is very comparable to lambda naught or less than lambda naught. So that becomes like this factor goes approximately very close to 1. Okay, or even if 10% of them are actually they are tunneling, there are a lot of carriers, right? A lot of 10 or 22 carriers are over here. Okay, so even if let's assume it is 10 to the power minus 3, then there will be 10 to the power 19 electrons, okay, tunneling through this junction. And that's why the tunneling current that increases, because the electrons are actually tunneling from this side. So the effective current will be from N to P side. Of course, in conventional current, you can see we have ID over here. So the current is like basically flowing in this direction. So you will get a curve. So if you increase the reverse bias, up to some time it will maintain a reverse saturation current Is, that is decided by the device parameter, okay, and the recombination rates. And then after some voltage Vz, there will be a sharp increase in current in the negative direction, Iz, or the Zener current. And this happens at around 2 to 6 volts. And if any of these conditions, that means if W is not very small, then this condition will not be matched and this will not happen. The breakdown will not happen, and if you keep on increasing the reverse voltage, this will continue up to the normal breakdown of material. So that is dependent on generally the silicon or germanium or gallium nitride. Large band gap materials, they have high breakdown voltage, but for silicon generally it varies. It is around 50 to 100 volts. Okay. After that, this breakdown will happen. However, this breakdown is avalanche breakdown, and because the lattice is almost like destructed, and that's why the diode cannot be used again. In case of Zener breakdown, it is a tunneling current, right? It's a tunneling current, and the electrons are actually jumping from one side to another side. There is no loss or damage to the junction or the crystal, and that's why once you remove the reverse bias, it will work as a normal diode. Got it? So here is the basic principle of what is Zener breakdown, why it happens, and also what are the conditions. So there are two conditions. Number one is that W should be very small, and for that you must have high doping concentrations on N side and P side. That's how you can achieve. Another condition is that sufficient reverse bias should be applied so that valence band on P side comes in line with conduction band on N side. Okay, so this condition. So of course it should be a little more, okay, because most of these will be occupied by P holes carriers, and some of the region in EC that will be electrons carriers. Okay, so even if they are aligned just like this, that these 2 points are actually coming across, tunneling cannot happen. Okay, so that is another issue that I will discuss in tunnel diodes. So of course in that case, in forward direction current will increase. Anyway, for tunneling, this is the condition, that it should be sufficiently reverse biased so that very high electron in the valence band, they should have a corresponding energy level in the conduction band of N side at the same energy states. Okay, and this happens generally for VR is equal to 2 to 6 volts depending on concentration on N side and P side. Okay, after this I would like to discuss one more important thing, that how this breakdown varies with doping concentration. Of course, as the doping concentration increases, W decreases, the junction width, and that's why you will find this curve. So here this data is taken from Benji's treatment. Okay, so and here for 4 materials, germanium, silicon, gallium arsenide and gallium phosphide is shown. You can see that at concentrations around let's say 4 into 10 to the power 17, you can have 6 volts. You can have a breakdown, Zener breakdown of 6 volts. This region is generally the Zener breakdown. This is Zener breakdown region. If the carrier concentrations are quite high, W will be less, and hence the probability that Zener breakdown will happen, that is quite high. So in this region, Zener breakdown happens, and if the carrier concentrations are small, then in this region, generally avalanche breakdown is more dominant. And you can see that avalanche breakdown can go up to 100 volts, okay, for carrier concentrations up to few 10 to the power 15, that is actually called the lightly doped, not very or nominally doped. For very lightly doped, if you want a breakdown voltage, avalanche breakdown voltage very high, you must have very lightly doped semiconductor. Okay, so if you want VBR to increase, reduce the doping concentration. That is also one of the requirement for having high VBR for space applications where the radiation are quite high. So all the circuits which we send to space like satellites and other, they are actually the radiation fluctuation that is quite high, and that's why we must have VBR rating very high. Some people also use wide bandgap materials. Bandgap materials for this application, because as the bandgap increases, this VBR increases. You can see that germanium has low bandgap, and hence its breakdown voltage is also small as compared to silicon. While gallium phosphide has higher breakdown bandgap, and hence the silicon will have gallium phosphide will have higher breakdown voltage as compared to silicon. Only the gallium nitride that has band gap of 3.4 electron volts, they are generally used for space applications. I think I covered most of the things related to Zener breakdown. Some circuit application I will cover in next lecture. Thank you.